Alright, well in this recording I'm going to do a walkthrough of the practice exam for exam 3, both to review the content and also to make sure that everybody knows how to enter their answers and their work. So let's go ahead and get started on that. Alright, so here we are in eLearn. I've put it in student mode, so hopefully everything is looking the same here as it would look for you. I'm going to click on Content, and then scrolling down I'll see Practice Exams, and I'll click on Practice Exam 3. Alright, and then I have to scroll down to the bottom of the screen. Now I disabled the lockdown browser feature so that I could make this recording. One of the things that the lockdown browser does is it keeps you from being able to record the screen. So I had to shut that off for this. So that's something you will have to do that you're not going to see here. But it's really just a matter of clicking on something and downloading that software. So let's go ahead and jump in. Start quiz. Apart from not having the lockdown browser going, this should look pretty much like it's going to look for you. All of the questions are in the form of long answer questions so that you can type out your answer and when it applies your work as well. Now for this first problem, it says state whether the series where n goes from 1 to infinity of negative 8 fifths to the 2n is absolutely convergent, conditionally convergent, or divergent. Okay, you don't need to provide a proof for your answer. Alright, so this one's pretty easy. I can just click in the box and type my answer. This one is divergent. Now how do I know? Well, I can see that it's a geometric series, and my R value, now technically my R value isn't negative 8 fifths, it's actually negative 8 fifths squared, because that's what's being raised to a power of n. But negative 8 fifths squared is bigger than 1. It's 64 over 25. Okay, so this one's divergent. Okay, since the problem says you don't need to provide a proof, that's all we need to do for question 1. Question 2, give a formula for the nth term of the sequence. Alright, looks like we have an alternating sequence, so we're probably going to need a negative 1 to a power. And it looks like our denominators are odds. Alright, now since I'm typing a formula on this problem, I'm going to have to come over here to the upper right hand corner of my question box and click on these 3 little dots. That expands my menu of things that I can insert in here. And one of the things I can insert is an equation. And I get to the equation editor by clicking on this little sigma symbol, which is kind of pertinent to what we're doing right now. Okay. Alright, so I want to say my nth term, that would be a sub n. So I'll type you got to click in the little box. I'll type in a, and then this command right here gives me the subscript n. And if I just arrow over, now I'm out of the subscript. So a sub n equals, alright, I'll type a parenthesis, negative 1. And now I want a power, so I'll click this symbol here, superscript. Now I don't just want n because sequences are assumed to start at n equals 1. And I want it to start with an even power so it starts positive. So I'll do n plus 1. That way in the very first term the power on negative 1 will be 2 and it'll start positive. And then let me see. I want to put all this in the numerator of a fraction, so I'll highlight it and I'll click on this little fraction symbol. And now for the denominator, remember we had just odd numbers, so we'll do 2n. Now if I do 2n plus 1, then when n is 1 we'll start on 3. But I want to start on 1. Now if you need to, you can always grab this box. Okay, you can grab it and drag it out of the way if you have to look back at the original problem while you're working. Alright, but that looks pretty good right there, so I'm going to go ahead and click Insert. Okay, there's my formula for the nth term, so good to go there. Now, as soon as I click out of that box, the quiz actually does save that answer. So even though there's not a save feature, you can see over here on the left, it's given me check marks for 1 and 2. So it's registered my answers for those two problems. Alright, question 3. State whether the series, where n goes from 1 to infinity and the nth term is negative 1 to the n over the square root of n cubed, is absolutely convergent, conditionally convergent, or divergent. You don't need to provide a proof for your answer. Alright, so we're just going to give the answer. Now, notice that if I applied absolute values to the terms, that would just turn the top into a 1, and the bottom would be square root of n cubed, or n to the 3 halves, which means that when I apply absolute values, this becomes a p-series with p bigger than 1. 3 halves is 1.5, and that would be a convergent p-series. So that means this thing is convergent even when I apply absolute values to the terms, so it's absolutely convergent. And I'm just typing in my answer. There we go. Alright, notice I clicked over here to the right and a check mark appeared right there. Hey, we're making good time on this one. Alright, question 4. Find the limit as n goes to infinity of the sequence whose nth term is a sub n equals the natural log of n plus 1 over the square root of n plus 1. Now notice this time it says show all work. Okay. Now, notice that both the numerator and the denominator go to infinity as n goes to infinity. So this is a problem where we can apply L'Hopital's rule. So I'm going to need some formulas. So again, I'll click on my 3 dots over here, and I'll click on my sigma symbol. Alright, now there's a special little menu up here, a tab just for limits and integrals. So I'll click my limit tab, and I want to limit as something goes to infinity. I have to click in that little box and type in an n. Alright, now I'm going to go back to my original tab so I can get the fraction symbol. I'm going to say the limit of the natural log of n plus 1 divided by, now notice there's a little square root symbol I can use, square root of n plus 1. Now I want to make sure I copied that correctly, so I'll just drag the whole thing over. Actually, when I drag it, it makes it transparent. Yep, looks like I copied it correctly. Equals, I think I'm just going to cut and paste this limit business so I don't have to retype that. And I want another fraction. And you know what? Up in the numerator of my fraction, that becomes a fraction. The derivative of natural log of n plus 1 is 1 over n plus 1. Now let me see down in the denominator. Well, that's actually a fraction too. Okay, it's n to the 1/2, which the derivative becomes 1/2 n to the negative 1/2. Okay, or we could put it like this. It's 1 over 2 times the square root of n. Alright, so again I'm going to cut and paste this little limit business. Equals the limit as n goes to infinity of, alright, so a fraction divided by a fraction. I got to flip the bottom fraction, which means this 2 square root of n is going to go up in the numerator. This n plus 1 is going to go to the denominator. And now I don't need L'Hopital's rule, I can just compare degrees. Okay, you could apply L'Hopital's rule again if you wanted to, but I don't really need to. The degree of the top is 1/2, the degree of the bottom is 1. Bottom has a higher degree, which means the limit is 0. Okay, you know what? Maybe just for the sake of completeness, let's apply L'Hopital's rule one more time. Oops. Oh, that's no good. I accidentally deleted everything. But there is an undo button. That's handy. I didn't mean to show you that, but I'm glad I got the chance. Alright. Let's let's just finish with one more application of L'Hopital's rule. So the derivative of the top, here the 2's would cancel, and I would actually just get the fraction 1 over square root n. The derivative of the bottom is 1. Alright, now I can clearly see that as n goes to infinity, this fraction is going to 0. Alright, so I'll click Insert, and there's my work and my answer for problem 4. Click outside the box, and now we've got a check mark for 4. Let's go on down here and make sure everything's recording properly. Yes, it is. Find the sum of the series. Alright, well, this is a geometric series. 2 to the n over 7 to the n is the same as 2/7 to the n. And that's an r value that's less than 1. So I can use my little formula. Okay. And I think I'm going to need the equation editor. So again, click my 3 dots. Click my little sigma to get the equation editor. Okay, I can use that a over 1 minus r formula. Okay, now r is clearly 2/7. So the bottom is 1 minus, need another fraction, 2/7. Now I got to be careful. It would be tempting to look at this problem and say, oh, what would a be? Well, it looks like there's nothing in front of the thing to a power, so a must be 1. But keep in mind, a is always the first term. So if you're not sure, think about what the first term would be. What's screwy about this one is that n starts at 1, not at 0. If n started at 0, the first term would be 1, and that would be our a. But since n starts at 1, our first term is actually 2/7, and that's our a value. A is always the first term. You can keep that in mind. That helps a lot. It helps me keep it straight. Alright, so let me see. That's 2/7 over 5/7. The 7ths cancel, and that's 2/5. So there's my work. There's my answer. Insert. Yeah, looks like we're half done with this test now. Yeah, we're coming along pretty good. Alright, question 6. Determine whether the series is convergent or divergent and provide a proof for your answer. Alright, so we'll have to do a little more typing here. But I'll tell you what, I can see that it's convergent because if I deleted the 5n and the 4, this would just be a convergent p-series. Okay, so let's do, this would actually be a good one to do the comparison test for, because when I delete that stuff, it actually makes the fraction bigger. So here's what I'll say. I'll click my 3 dots, I'll click my sigma, and I'm going to reproduce that fraction. So 1 over n. Now I need a square, so I'll click my superscript button, and then I'll arrow over to get out of the superscript. 1 over n squared plus 5n plus 4. Yep, I'm just making sure I copied that right. And there is actually a symbol for less than or equal to, but you know what, I can actually use the less than symbol on my keyboard. Okay, or you could use a symbol from over here. That's less than 1 over n squared. Okay, let's go ahead and hit insert, and we'll say 4. And then we want to say n greater than or equal to 1, so I'll just go back into my equation editor and say 4n, and I'll click my little greater than or equal to button and type a 1 and click insert. But what else do we want to say? Let me see. I'm going to use the comparison test, so I need to make sure I check off the conditions. Well, the other conditions are that it's positive and decreasing. It's clearly positive, and it's clearly decreasing because all the signs are positive. So I don't really need to prove any of that per se, but I do need to state it. So let's kind of slip that in there. So we'll say comma, and it is positive and decreasing for n greater than or equal to 1. Okay, so that's everything I need to be able to use the comparison test. Now I need to say that I'm using the comparison test. So by the comparison test, this series is convergent. Did I leave anything out? Oh yes. We'll just slip this in. Also, so I need my equation editor. I think I want to do a sigma symbol. There's a tab just for sigmas. So also the sum where n goes from 1 up to, now there is a symbol for infinity, and I can see the tab that has the infinity symbol. And let's go back to our first tab. 1 over n squared. Aha. So also, this series is a convergent p-series. So by the comparison test, alright, so now I need to be explicit about my original series. So my final conclusion is about the original series. So you know what, I'm gonna click on this to highlight it, and I'm gonna press Control C, and over here where I typed this series, I'm gonna delete that and I'm gonna paste this in, and then I'm gonna click on it again and go back and click on my equation editor symbol, and I can make this plus 5n plus 4. That looks a lot better. Okay, so by the comparison test, the series where the nth term is 1 over n squared plus 5 to the n plus 4 is convergent. Click. Alright. Notice, actually I hadn't noticed this before, but when I clicked outside the box, up here it actually tells me saved. Okay, it just changed to saved. Alright. 4 more questions. Give an upper bound for the difference between the infinite sum. Oh, so this is the p-series we were just talking about, where the nth term is 1 over n squared, and the partial sum where n just goes from 1 to 1,000. So we've talked about 2 different circumstances where you can get an upper bound on the error or the difference between an infinite sum and a partial sum. If the series is an alternating series, then you just take the absolute value of the first term that you didn't include in the partial sum. That's pretty easy. This is not an alternating series though. All the terms are positive. Okay, in this case, where all the terms are positive and decreasing and going to 0, we said that you could take an improper integral that starts right where n left off. So our improper integral will actually have to start at 1,000 and go to infinity. Okay, and we'll just be integrating 1 over x squared. So let's go to our 3 dots, open our equation editor. So we're looking for an integral that has its own little tab over here. Okay, I kind of like this little template right there. So it's an integral from 1,000 up to infinity. So I need to click that little infinity tab. And then I need a fraction, so let's go back to the first tab. So that'd be 1 over x, oops, just 1x, but it needs to be squared, dx equals, alright, so we've learned previously that to do an improper integral, we really need to do a limit as b goes to infinity. And then I'm just going to copy and paste this because oops, let me click my little undo there. I'm going to copy and paste and just change that little infinity to a b. All right, equals, and now I'll copy and paste my limit. Okay, so let me see here. Ah, yes. Let's let's put everything in a box just so that we can preserve the limits of integration of 1,000 and b. I can't click in the little box. Well, that's annoying. How about we do this? I think the problem was I was not clicking very precisely. All right. Well, let's just use some parentheses then. We'll get our parentheses, and then in the parentheses we're going to have two fractions. There we go. Now the antiderivative of 1 over x squared is negative 1 over x. So my first fraction is negative 1 over b. And then we're subtracting negative 1 over 1,000, so really plus 1 over 1,000. And of course, since we're taking the limit as b goes to infinity, that first fraction will go to 0, and the limit will then just be the second fraction. Oops. Copy the 1 over 1,000, paste that in, click Insert. Alright, and that's it for problem 7. 3 more to go, 8, 9, 10. Alright, determine whether the series cosine of pi n e to the negative n is convergent or divergent, and provide a proof for your answer. Alright, well, as we mentioned before, sometimes sine and cosine generate alternating series. Let's think through this a little bit. If n is 1, we get cosine of pi, which is negative 1. But if n is 2, we'd get cosine of 2 pi, which is positive 1. If n is 3, we'd get cosine of 3 pi, which is the same as the cosine of pi, it's negative 1. So yeah, this cosine of pi n just serves to give us an alternating set of coefficients that are either negative 1 or 1. So I'll capture that by just saying this. Okay, I'll say cosine of, now I need a pi. I think pi is, oh, it's here in my first menu. Cosine of pi n equals negative 1 to the, now let me see, it starts out negative, and n is starting at 1, so yeah, we'll just do negative 1 to the n. Okay, so cosine of pi n is really the same thing as negative 1 to the n, so this is an alternating series. Starts negative and it goes negative, positive, and so on. Okay, now if it's an alternating series, then I can focus on the rest of the term. I can ignore the part that's really negative 1 to a power and focus in on this e to the negative n. So let me see, e to the negative n, well, of course that's really 1 over e to the n. So that is positive, decreasing, and let's say it. So it's positive and decreasing. Okay, positive and decreasing for, go back into my little equation editor. Positive and decreasing for n greater than or equal to 1. So this is really what I'm looking for here. I'm trying to model what you guys should be doing. I'm checking off the conditions of using this particular test. Okay, so I need to know that the absolute values of my terms are positive and decreasing, and so I'll go back into my equation editor, and the limit as n goes to infinity of my little fraction here, 1 over e to the n, is 0. I'm using the alternating series test, but to be able to make use of the alternating series test, I need to know that my terms are decreasing and that their limit is 0. Okay, and of course I need to know that it's an alternating series. Okay, so I've taken care of all of the conditions. So I'm ready to say what test I'm using and what my conclusion is. So, by the alternating series test, and this time I think I can say this series. I've only talked about one series, the original series, so that shouldn't be unclear here. This series is convergent. Alright, that knocks out number 8. That one's saved. Let's go on to number 9. Find a power series centered at x equals 0 for the function f of x equals x squared over x plus 3. Write your answer with sigma notation. Also, give the interval of convergence. Alright, so I'm going to reproduce that little fraction. X squared over x plus 3 equals, and now I'm going to start manipulating it, so I'm going to copy it. Okay, the 3's got to come first. 3 plus x. Alright, that's an easy manipulation because the order of addition it's commutative. We can change the order. Okay, but I really need that 3 to be a 1. Okay, because I'm trying to make this match up with that a over 1 minus r form. Well, the only way to get that 3 to be a 1 that I can think of is to divide everything by 3. I mean, I guess I could split a 2 off of it, but then I would wind up being centered somewhere else. Okay, and the problem specifically says centered at 0. So I like not having anything added or subtracted with this x. Alright, so I'm going to divide everything by 3. So that x squared, I want to put that in a fraction, put that over 3. And I'm going to put that x in a fraction and put it over 3. And 3 over 3 is 1. Alright, but then there's one more thing. I need it to be 1 minus. Okay, well, I can do that. I can just make it minus a negative. So let's put this in parentheses. Click the little negative. Alright, looks like we're in pretty good shape now. Okay. Well, so now I can clearly see that my a is x squared over 3. And I can see that my r is negative x over 3. Okay. So now, applying my formula, I can say that this equals a summation where, let me see, n is going to start at 0 and go up to infinity. So we have to click our little infinity tab. Okay. N starts at 0, goes to infinity, and then this is my A, so I'll copy it over here. Okay, and then I need to say times. Well, you know what, I can, if I leave this stuff in parentheses, that'll communicate the times part. Yeah, but I need to give that a power of n. Alright. Now that is my power series. But generally we like to have x to the n by itself. So we'll apply the n to the negative. That gives us a negative 1 to the n. So let's just cut and paste. Say equals one more time. So let me see, we're going to have a negative 1 to the n. And then that allows us to take the negative out of here. And we also have a 3 to the n because of this 3. And this is a 3 to the 1. 3 to the n times 3 to the 1, we add the powers. That becomes a 3 to the n plus 1. And now, all that's left in parentheses is my x. But you know what? I don't want to have this other x squared hanging out here. I need to combine that with my x to the n. And if I do that, again, I can add the powers. And that becomes n plus 2. And then I can just make this numerator 1. And you know what? If I just took this negative 1 to the n plus 1, I could stick that up in my numerator, and that makes it all a little cleaner. Boom. There we go. I think I made that a little long. I'll tell you what. Let's move part of it to the next line. Alright. Well, we can see that anytime we want to by opening it up. Okay. Now, let me see here. Oh, you know what? I know what might be good. That part that I moved to the next line, let's just leave that out entirely, but I copied it. Aha! And then I'll go in and I'll open an equation here on the next line, and I'll paste in that stuff. There we go. There we go. Now it's all visible. Now I'm almost done. Okay, I'm almost done. I've written the power series. Okay, it's centered at 0. I've written my answer with sigma notation, but I also need to give the interval of convergence of the power series. Well, remember my r value was negative x over 3. So I need to put that negative x over 3 in between negative 1 and 1. Alright, so negative 1 is strictly less than x over 3, and that is strictly less than 1. Now the reason I'm using strictly less than is because this is a geometric power series. For a geometric power series, r has to be strictly between 1 and negative 1 to get convergence. Now, let me see, if I multiply through by negative 3, that's going to reverse my directions. Okay, so that's going to give me 3 is greater than x is greater than negative 3. So, the interval of convergence is, I don't really need the equation editor to write this. I can just type it. It's the interval from negative 3 to 3. Alright, one more problem to go. Okay, determine whether this series is convergent or divergent and provide a proof for your answer. Well, notice there's an exponential part, a constant raised to a power. If that was all there was, this would be geometric, and I wouldn't have to think about it any harder than that. I could just use what I know about geometric series. Okay, But I have a combo here. I've got a fraction where the top is geometric and the bottom is polynomial. Okay, it's kind of the opposite of geometric. It's variable to a constant power. Okay, to sort that out, I'm going to need the ratio test. Okay, so seeing an exponential factor like this, but also other types of factors, is a good clue you should use the ratio test. So we're going to have to do some limits here. So I'll use my limit tab. Limit as n goes to infinity of, now in my parentheses here I have an absolute value. Remember, we need to use absolute value for the ratio test. Okay, now remember we start with the n plus 1 term, so we want 2 to the n plus 1 over n plus 1 to the 4. And then we multiply by another fraction, so I can use this little multiplication symbol. Toss in another fraction. This one will be n to the 4 over 2 to the n equals limit. You know what, let's copy the whole thing. Okay, but let me see, 2 to the n and 2 to the n plus 1 and 2, I subtract the powers, that leaves me with just a 2 and a 1. Okay, and you know what, n to the 4 over n plus 1 to the 4, I could multiply this out. Okay, but if I multiply this out, the leading term is going to be n to the 4. So n to the 4 over something that starts with an n to the 4 is a rational expression where the top and bottom have the same degree. So I just need to take the ratio of the coefficients, 1 over 1. Well, that part just goes to 1. So this limit equals 2. Okay, because the rest of that stuff goes to 1. So by the ratio test, there's not really a lot of conditions to check for the ratio test. Okay, the only condition is that none of the terms are 0. Okay, so we could toss that in there. Okay, so maybe throw that in. Note, yeah. So we'll type up our nth term there. So note, 2 to the n over n to the 4 does not equal 0 does not equal 0. So it's significant that n starts at 1, okay, up in our series. So it does not equal 0 for n greater than, oh, I lost my n there, n greater than or equal to 1. Alright, so now we've checked all the conditions and we can actually use the ratio test. So by the ratio test, our series is, well, for the ratio test, if this limit comes out to be anything greater than 1, that means our series is divergent. If it comes out to be less than 1, our series is convergent. And if it turns out to be exactly 1, then the test is actually inconclusive. But a limit of 2 is conclusive. By the ratio test, our series is divergent. Alright, well, we've got all 10 problems done. Took 38 minutes. Okay, I might have over-explained a few things, but I think we are good to go. So submit quiz. You're about to, yep, that's what I want to do. I want to submit the quiz. All right, we are done. All right, well, that's all there is to it. So I'll leave it at that. But as always, if you have questions about anything, please let me know. Take care and good luck, everyone.